So let's start our new topic, stress concentration. In the last few classes, what we have discussed on the theories of failure and stress concentration is basically continuation of that. In this particular topic, what we are going to learn, basically we'll try to clear the concepts of stress concentration. We'll learn the importance of stress concentration in design, and at the end of the topic we'll see how to do some of the practical designs using the stress concentration consideration. So let's start and try to understand what we mean by stress concentration. Here in this slide, what you can see is the plate which have some kind of discontinuity in it, and these are very common in different kinds of machine components. They have holes, they may have fillets, may have notches, and because of this kind of discontinuities, around those discontinuities basically stress concentration occurs. Let us try to define what we mean by the stress concentration. In the theories of failure, what we have learned is that we have learned that how to apply the different failure theories to design a particular component. And in doing that, what we actually did is that, suppose there is no hole in this plate and we want to design it, then what considerations we'll do? So we'll basically consider that under this external load which is acting axially on a plate, because of that some stress that will occur in this plate, and we'll see that what is the maximum value of the stress. And here you can see if there is no hole, it is uniform. So based on that maximum value, we set some criteria of failure, that if it is less than the strength of the material, then it is safe. But actually what happens if this kind of discontinuities in the geometry present in the machine components, then around that discontinuities, whether it is notch or fillet or hole, some stress that created is much higher than the far field stress. Here you can see this particular section is far away from this hole, and here it is quite uniform, but here very near to this hole the stress is quite larger than this one. So this is what is called that stress concentration. And because of these holes or the notches or the fillets, basically what happens, this maximum stress close to these sections are very high, and these are what is called the stress concentration. Now let us try to understand what we mean by that, or how this actually happens. Let's take some color. Okay, now first thing is that if we do not consider this kind of sections where the chances of stress concentration is there, then what happens? If we only consider the far field stress, and based on that if we do the design, then obviously we underestimate the actual local stress, and our design will not be safe, because there is always a chance that around this section where the stress will be maximum will be more than that, and before our prediction it may fail close to these sections. Now here I have given some of the examples just to give you some idea that how stress concentration occurs in different kind of geometrical discontinuities in the members. There are many other sections or the form of the stress concentration or the stress risers are possible. Okay, so now let us try to make an analogy with the flow field. Okay, if you consider this is a pipe where here you can see the section is very large and here the section is small, then if the fluid is flowing, then what will happen? Then obviously the fluid will try to adjust itself and then it will flow through the small cross-sectional pipe. And in doing that, around this region, obviously the streamlines will come very close to each other if you compare with the other regions. So the same thing occurs in case of force field also. If you consider this is a plate where the section is changing abruptly in this particular figure you can see, and if this particular component is under axial load along with this, then what will happen? From this end to this end, continuous force field can be thought of. These are called the flow lines. Okay, these are called stress flow lines, and these are continuous lines. They cannot be discontinuous. Here the section is suddenly, there is a discontinuity in the section. Here you can see that sudden change in cross section, but the flow lines, remember, are always continuous. And due to this, what happens in this region, or in this region, what you can see is that the flow lines are very dense. They are crowded around this corner. So number of flow lines per unit area gives an idea about the stress concentration. Okay, so looking at the flow lines, we can get some idea about how much will be the stress concentration. Now if you compare this figure where the abrupt change of cross section is taking place, and this figure where the cross sectional change is gradual by providing a fillet radius, which is commonly done, this kind of abrupt changes are not suitable because the stress concentrations are very high. So anyway, but still here you can see that the lines are very close, but if you compare with this one, it is less. That means the stress concentration will be less in this particular component. So it's a better design with respect to this one. But again, if you compare in this particular component far away from this fillet, that means in this region or in this region, you can see that concentration of the flow lines are higher in these regions. That means with respect to this region or this region, there is a stress risers present over here, and that is why stress concentrations are present. Okay, so we cannot totally ignore the stress concentration effects when we are going to design. Okay, so now here in this figure you can also see that there is a plate and it is also axially loaded as shown in the figure, and there is a central hole like this. So the flow lines that will be continuous from one end to the other end, you can see the flow lines will look like this. So it is very clear from this picture that the stress will be concentrated in these regions. So stress concentration will be very high. Okay, so this is what we actually mean by the stress concentration. So if you see, if you want to see that how stress concentration actually, because of the stress concentration, the distribution of stress, if you draw a line, that means along this section, if you want to see that how the stress field will vary, it will be like this. That means you can see as you go away from that hole, the stress is small, and very close to the hole, the stress is very high. Here you can see the stress is very high, large stress, whereas here far away the stress is gradually decreasing. Okay, so similar thing will be in this section also. So this is what you can see, the maximum stress that will be developed very close to this kind of discontinuity. Here in this case it is the pole. The similar thing will occur in case of notches, fillets or other changes if that is there in the component. Okay, so now try to see that how the materials behave under the stress concentration. So we have given a name that when consideration of stress concentration is important, that means whether it is important for all kinds of material, ductile or brittle. The answer is that in case of ductile material, if it is under static load, then it is not so important. If the material is ductile and the loading is static, then stress concentration consideration is not so important. But if the load is dynamic, that means if the magnitude or the direction of the load is changing with time, that is what is called the dynamic load. That means the load which is acting, on the element, if that is function of time, which is called dynamic load, then whether it is a brittle or a ductile material, stress concentration is very, very important. Then stress concentration has to be considered, okay, if it is dynamic load. But if it is a static load, that means with respect to time the load that is applied is not changing, that is called the static load. If the load which is acting is not function of time, if that is not function of time, which is constant basically, that is called the static load, okay, which is called the static load. Static. Basically the examples that I have shown you here, if this load is not changing, if these loads are not changing, constant pull is there or something like that, in that case the loads are considered to be static. In fact, in the theories of failure we have solved many problems. In almost all the problems whatever we have done are under static load. In fact, in your strength of material course also, most of the problems that you are doing, 95% problems that you are doing are static design that you are doing. Okay, so dynamic load, we'll discuss dynamic load in the next topic on the fracture mechanics, definitely in detail, how stress concentration is important in dynamic load and all that. But right now only takeaway points from this slide is that if it is dynamic load, then stress concentration is very important irrespective of whether it is a ductile or brittle. Second point, if it is a static load, then in case of ductile material it is not so important. That means stress concentration can be ignored in case of static loading under static loading for ductile materials. The reason is that since you know that in ductile material a substantial amount of plastic deformation takes place. So what happens actually around the stress risers, what happens, since the stresses are very high and if they go above the yield point, then local plastic deformation takes place in case of ductile material, and that again redistribute the stress, and that is why some amount of stress can be relieved, and that's why it is not so dangerous. Some crack may form, but the chances of those cracks to be stable. Anyway, what is crack and how it propagates, that we'll discuss in the next topic, not in this topic. You just remember that for static loading, if the material is ductile, then stress concentration can be ignored. Okay, this is very important point. But if it is a brittle material, whether it is a static or a dynamic load, stress concentration has to be considered. Okay. Now let's come to the most important point, that how can we calculate the stress, what will be the maximum stress. Here you can see this example where there is a hole in a plate and the plate is loaded axially as shown in the figure, and if you see the variation of stress across the section where the hole is there, you see that the tip, at this tip, or that means close to the hole, the stress is very high, and as you go away up to the edge of the plate, gradually the stress is decreasing. So how the stress is distributed is shown in this figure. Now what is our what we want to find out here? We want to find out what is this maximum stress. Remember, in any theories of failure, whether material will fail or not, that depends upon what is the maximum stress. So our objective is always to find out the maximum stress. So here the maximum stress will occur where there is a chance of stress concentration. So we want to calculate this maximum stress, and to calculate the maximum stress we'll use this simple formula. That means maximum stress will be equal to some constant Kt, which is called the stress concentration factor. This T basically indicates tip. T indicates tip, that means at the tip of the stress concentration, where the stress concentration is taking place. That means here in this case the hole or the notch or whatever that may be at the tip, this is occurring. Okay, so Kt is basically called the stress concentration factor, and that is equal to sigma max divided by sigma nominal stress. Okay, so maximum stress, you can see the maximum stress can be calculated as some Kt, which is stress concentration factor, into the nominal stress. Nominal stress is basically the average stress. What is the average value? It is not the smaller one, it is the average value. So multiplied by the mean stress or nominal stress or the average stress. There are many names of this one. Okay, so nominal stress. So this is what is the nominal stress. Now how can you find out this nominal stress? To find out the nominal stress, let us take this particular example, then the idea will be clear. This nominal stress can be calculated by what is the load acting. The load acting is P, and what is the area that you are going to consider to find out the nominal stress, because this is the average one. So at this cross section where the hole is there, you have to consider that section. So what is the width of this section? The total width is B and the hole is D. So the remaining portion is what? So B minus D. Okay, so B minus D, this is the effective material present along the width at this section multiplied by the thickness. If the plate is, suppose the thickness of the plate is T, if T is the thickness of the plate, so B minus D into T. So this is what is the area that you have to consider at that section. So this is basically the average, that means the total load divided by the area on which the material is there. So P by B minus D into T, this is what is the area. And if you do that, you will get basically the average stress which is acting at that section. But interestingly, you see the maximum stress which is occurring at the tip is more than this one. So how many folds it is more, how many factor it is more? So that thing is simplified by considering this Kt. So maximum stress will be this Kt times of nominal stress. So first you calculate the nominal stress. If you know the load and the dimensions, then you multiply it by the Kt. The question is where from you will get this Kt, the stress concentration factor. Okay, for that there are tables, and from those tables we will find out the values of Kt, and if you know the values of Kt, it is very easy to find out the maximum stress. Okay, So I think the only thing that you have to remember is this formula, how to calculate the maximum stress. The most important thing is how to calculate the nominal stress is very, very important. At which section you are taking, what is that area, okay? So in that way you have to calculate, and you have to be very careful in calculating the nominal stress. And KT also generally found out from the different graphs you will find, different curves you will find in the handbooks. From that you have to choose the proper diagram. I'll show you that how we can select KT. Now here some of the points are there. You just quickly going through these points. Dependent on irregularity, dimensions of irregularity, overall dimensions, loading, these are the factors on which stress concentration depends. Okay, so stress concentration factor KT depends on these things. Basically it depends on the geometry. Stress concentration factor depends on the geometry. Then obtained experimentally, analytically, different way it has been observed. Okay, so it is very important in brittle materials. You see, in brittle material, whether it is a static or dynamic, it has to be considered. Ductile materials, important in fatigue calculation. Fatigue calculation means when the load is dynamic, then this kind of failure occurs, and we'll discuss that in the next topic. Okay, so under dynamic condition only for ductile materials is important if safety is critical. Even for static condition sometimes it is considered, but it will basically over design the whole thing. But if safety is the ultimate criteria, then sometimes we are very, very conservative, and we also consider stress concentration in ductile materials also. I have already mentioned you that why in case of static loading ductile materials stress concentration factors are not considered, because of the localized yielding basically hardens the material and redistribute the stress concentration, and that is why we neglect the effect of, most of the cases we neglect the effect of stress concentration in case of ductile materials. Remember, for static loading only. Now what I have told you, that here you can see this is basically KT, and these KT values are shown. And how can we find out KT values for this kind of loading? Suppose there is a plate, and the plate is loaded axially like this, and some hole is there, and if the hole diameter is like this and width is like this, then how can you find out the KT values from the graph? This is the guideline. Now you see this one, you see the KT values. This is again the KT values, the same KT values, stress concentration factors, but here it is not the hole, it is basically the fillet. You can see a larger cross section is reduced to a smaller cross section, some fillet radius is provided. So for this kind of cases, depending upon the value of R and the other dimensions, how KT is changing, that graph is this one. So all this will get in the handbook. For depending upon the different kinds of loading, different kinds of geometry, the KT values are basically listed or graphically listed. Here you can see a stepped pin which is under pure torsion, and when it is under pure torsion, again fillet radius is provided. These are the source of stress concentration, and the KT values here also, the KT values can be calculated from this graph. So depending upon the loading, you can see that it is saying here it is a torsional load. Okay, and the similar kind of thing you can see, maybe this is a shaft, but it is under bending. Okay, so again the fillet is there, but because of bending, these KT values may be different, and that will be guided by this graph. Okay, so we have covered almost what was needed to solve few problems, some problems related to the practical design, where we have to consider the effect of stress concentration. Let us take the first problem, where it is a bar. You can see this is the bar, and here you can see that its dimensions are given. Here this is A, this is B. Here some source of stress concentration is there, the fillet radius. This is the fillet, one source of stress concentration, and there is another source of stress concentration, hole. So two kinds of stress razors are present basically in this particular problem. Okay, let's see what is the problem. It's a 3 millimeter thick bar. Which dimension is 3? Basically perpendicular to the screen, if you observe. So maybe this particular dimension, if we see, then this dimension is 3 millimeter. Okay, so this dimension is 3 millimeter. If we call this as T, this T is 3 millimeter. Okay, it is actually loaded. Here you can see the 15 kilonewton. Basically the load that is applied, 15 kilonewton, and the bar has 10 millimeter. Bar has 10 millimeter hole. Here basically the diameter is 10 millimeter. D. Diameter is 10 millimeter. Okay, 10 millimeter hole. The question: determine the stress concentration factor. So what you have to find out is the KT value. Is the first part of the problem. Find out KT for each stress risers. What we mean by each stress riser? There are two kinds of stress riser. One is fillet. This one is fillet, and another one is hole. Another one is hole. So for fillet, if we give a name, this one that you have to find out, you also have to find out KT value for stress concentration factor value for the hole. So this is the first part of the problem. Okay, so let us try to solve this one. So what is the thing? How can I find out this one? I have told you we can find out KT values directly from the graph that we observe in the handbook. Okay, so if we go to for the fillet, first let us find out for the fillet. So go back and see where this kind of thing is there. Which one is it? This one. So if it is under axial loading, we want to find out the stress concentration. So from this graph basically we will be able to find out the KT values. So what is the H, capital H? You see each of these curves are corresponding to some H by H value, and the x-axis is corresponding to R by H value. So you have to know what is the H by H in our case and what is this R by H in our case, right? So let's see what are these quantities. So H, in this case this one is H, capital H, right? And that is A, and A is what? 60 millimeter, and B, that is small h, and that is 40 millimeter. It is 40 millimeter. And what is the radius? Radius of the fillet? Radius of the fillet is given 7 millimeter. So this is 7. Okay, so now use these values to calculate what is H by H and what is R by H. So H is 60. In our problem it was given A and B, so it is 60 by 40. Okay, so what is 60 by 40? Tell me. This 3, 8, sorry, this is 1 Clear? So we have found out what is h by h, that is 1.5. So where is h by h 1.5? This one is 1.5. So we have to consider this curve. So this curve is corresponding to 1.5. Okay. Next, we'll find out what is r by h. We have seen that in our case, this is basically capital R and small h is nothing but b. So R is what? 7 millimeter, and B is what? That is 40. So 7 by 40 is what? If we just calculate 7 by 40, 7 by 40, we are getting 0.175. So this is coming 0.175. So where is the point? 0.15, 0.2. So 0.175 will be exactly midway. So now if we go exactly middle up to 1.5, this curve is 1.5, exactly middle. That means it will cut here and it will be just below to this point. It will be close to this one. So what will be this one? 1.7, 1.75. Okay, so it is around 1.75. 1.75. So we have found out the value of KT, and that is 1.75. So one problem we have solved, that this will be 1.75 that we have got from the graph. Now to find out KT for the hole, we have to see this kind of a situation. So here the hole diameter, remember, 10 millimeter, and this side is what is 60. A is 60 millimeter. Okay, let's check. And P, load, external load P, that is 15 kilonewton. Okay, so see where is the situation. Okay, here is the situation. No, it is not, it is a 4. So this one, right? So here you see that what you require. You require this quantity, 2r by w. What is r? R is the radius of the hole, and what is w? This. So in our case, this r, 2r is basically d, that we have given the name, and w is in our case is a. So this quantity is coming what? D was 10 millimeters and A was 60 millimeters, right? So what is 1 by 6? 0.167. So it is coming 0.167. So if you plot 0.167, where it will be? Here 0.1, here it is 0.2. So each one is 1, 2, 3, 4, 5. So this is 1, 2, 1, 4, 1, 6, 1, 8. This is 1, 7, close to this one. So that means it will be around here. Okay, so this one. So what is this? Here it is 2.4. So 2.4, 1, 2, 3, 4. So 2.4, 2.45, 2.5. Okay, so this value is 2.5. So we found out that what is the stress concentration factor. So 2.5. So we have solved the first part of the problem, where finding problem is to determine the stress concentration factor for each stress stresses. Second part of the problem is find the maximum stress at each geometric discontinuity. Okay, so you have to find out what will be the maximum stress that will occur at this fillet and the maximum stress that will occur at this around this hole. Okay, to do that, let us see that what will be this one for the fillet. First do it for the fillet. Okay, so let's write the formula for the maximum stress, and what is that? That is Kt into nominal stress. Okay, so now we are solving it for the fillet. Case 1, we are solving it for the fillet. So in the table of Kt, you see that which area they have considered, and that will definitely help you to understand. Here you can see that sigma average considered as P by B into H. B into H, that means this is H, the smaller one, smaller cross section dimension, into B is the thickness, basically the perpendicular to the screen. Okay, so that is basically considered to find out the nominal stress. Average stress is nothing but the nominal stress. Okay, so we'll also do the same. So Kt value already we have found out, that is 1.75 for the fillet, and nominal stress is what? Nominal stress is P, that is 15 kilonewton. Nominal stress, sigma nominal, is P divided by B into T, where T is basically the thickness. That means in the perpendicular direction, the value in the perpendicular direction, T, thickness, this thing. So that is equal to what? 15 kilonewton divided by B. B, you know, it is 40 millimeter, right? So 40 millimeter. This is kilonewton. This is 40 into T is what? T is 3 millimeter thick, if you remember. 3 millimeter. Okay, so if you do this calculation, you will get that what is the answer, and if you do that, you will get 1.75 into 15 is equal to this divided by 40 divided by 3. So it is coming 0.218 0.218 kilonewton per millimeter square. Kilonewton per millimeter square. So this is the maximum stress that is coming considering fillet. Now if you consider the hole in a similar way, let us do it quickly without much explanation, because you have understood, I hope. That is again Qt into sigma nominal, and sigma nominal is what? That is P divided by what is the Kt value that we have seen, that Kt value is 2.5 for the hole, and what is sigma nominal, that is 15, that is load, divided by remember the area that you have to consider here. So the total length is A minus D, right? That is this length multiplied by T, thickness T. So the area that you have to consider is A minus D into T. This is the area that you have to consider. Okay, so if you do the calculation, you will get 2.5 into 15 divided by A minus D is 60 minus 10 into 3. Okay, so what is the final result? Let's check it. 2.5 into 15 divided by 50 divided by 3. Okay, so it is coming 0.25. It is coming 0.25 kilonewton per millimeter square. Okay, so you can see our solution is complete, because the second part was find the maximum stress at each geometric discontinuity. Okay, so I hope you have understood the problem. Now this is another problem. So here you can see a similar kind of bar, a bit different, where in both end different sectional dimensions are there, 3 different steps are there, and one hole is also there. Again, loading is axial loading. So the question is, a straight flat bar 6 mm thick. Again, the thickness of the bar which is given, so that is given T, that is 6 mm. Hole 18 mm diameter, so D is given 18 mm. D is given 18 mm. B1, B2, B3, all these sectional dimensions are given, and the stress concentration factors for the left fillet. So this is the based on this radius of curvature. If you consider that radius of curvature is some say R prime, and this radius of curvature is say R double prime. Actually these radius of curvature values are not given. If those are given, then from the charts we know that how to calculate the stress concentration factor, but here it is in favor of you that you need not to refer the chart, you can directly get this value. So these are given in the problem. So stress concentration factor in the left fillet, in the hole, and in the right fillet corresponding to this. So stress concentration factors are given. It is given that the allowable stress is 41 megapascal. That means that you cannot, the stress anywhere cannot be more than 41 megapascal. This is the allowable value. Okay. Then what is the permissible maximum load that you have to find out? Okay. So P max that you have to find out such that anywhere in the member the load, the stress cannot exceed 41 megapascal, because that is the allowable stress. So what you do? It's very simple. You know that what are the critical points? The critical points obviously are the stress risers. So these are the critical points, right? So find out the maximum stress here, find out the maximum stress here, and find out the maximum stress here using the stress concentration formula. You know that how to find out maximum stress. But one thing you do not know, that is what is the magnitude of P. Since you do not know the value of P, if you write the formula, your maximum stress will be in terms of this P, right? So let us do this exercise and see what we are getting. So if you do this calculation, so we know that maximum stress here, this M corresponds to the nominal stress. Okay, this M corresponds to nominal stress or the mean stress. Basically, sigma nominal is equal to sigma M. This M indicates mean stress. Okay, M indicates mean stress here. In this problem, this M indicates the mean stress or the nominal stress. Same thing. Okay. So what we know, the formula that we know is that how can we find out sigma max? We know that sigma max is what? That is Kt into what? Nominal stress, right? And what is nominal stress? Kt into nominal stress, sigma nominal stress. Okay, so what we know is that in this nominal stress you can find out, you can see this nominal stress is what? This nominal stress is P. If you consider that the load is P, then that divided by the cross-sectional area. That cross-sectional area depending upon that which stress razors you are using. So that will be what? P divided by, if you consider this one, then you have to consider B1. Then you have to consider B1. So B1 into T. So sigma N will be P by B1 into T. Okay. Now if you put this value, but you do not know what is P. But what you know is what is the sigma max allowed in the material. The sigma max cannot exceed the allowable stress. Okay. So in place of sigma max, you can directly put the value which was given for the maximum value, that is 41. So you just put sigma max as 41 and you put Kt. Kt was given for this fillet. For this fillet, what is Kt that is given? You put in place of sigma N B1 and T, but you do not know what is P. So from this equation, you see you know everything other than P, so you can find out that P. And if you give the name of that P as P1, so that P1 will be according to this formula. The same thing you will get. Okay, the thing is very simple. It is the formula that we have learned. What we are going to put in place of sigma max, we will put the allowable stress. In place of Kt, the Kt values are given. Okay, and in place of sigma N, we will consider the corresponding area to calculate that stress depending upon whether it is a hole or a left fillet or a right fillet. Okay, so similarly for the hole, if you want to do the same calculation, what you will do? The formula will remain same. Only thing that is going to change is that sigma N you have to put what? For the hole. For the hole, sigma N will be equal to P divided by what will be the area? B2 minus D. B2 minus D into T. So these will be the area that you have to consider when for the case of hole. Okay, and P you do not know, so P will remain there in the expression, but the denominator you know completely. Kt for the hole you know. Sigma max again we are going to put 41 because that is the maximum allowable possible, and we will get some value of P. Finally what we will check, we will get in this way, if we consider for these two fillets and the hole, we will get three different values of P, and among them which one is minimum, that is the allowable maximum load that can sustain this member. okay, because it cannot sustain more than this one. And what we are observing, it is happening for the hole. So stress hole is more dangerous stress stresses if you compare in with respect to these fillets. Okay, so the maximum load it can take is 3.45 kilometer. Okay, so I hope you have understood this point, and this is the way by which we can find out the safe load, or basically we can design for the safe load considering the effect of stress stressors. Okay, now there is another problem. This is the third problem, and here you can see there is a round bar and there is no stress concentration present here, and it is loaded by P1. Here is another bar where two fillets are there loaded by P2. What is the problem? Dimensions are given. It is compared with a bar of the same diameter which has an enlarged portion with a diameter D to 25 mm. The radius of the fillets is 2.5 mm and the associated stress concentration factor is 1.74. So both the fillets are similar, and consider the stress concentration corresponding to this fillet is 1.74. Okay, does the enlarging of the bar in this manner make it stronger? So this is a bar, and now what we have done, basically we have increased the cross section here. You see here it was only D1, now the cross section has been increased D2. So apparently you get an idea that okay, if the cross section is more, probably this is a much stronger component if you compare with this one. Let's check whether this is stronger or not. Okay, so let us find out what is the permissible load P1 and permissible load P2 for these two components, and if we find that P2 is more, that means this much, this one will be stronger definitely. Okay, so this is not a very difficult one. So how to solve the problem? It is given again, the allowable tensile stress of the material is 80 megapascal. So maximum allowable stress, that is given, exactly similar what we have done before. So you know what is the sigma max. Okay, so for this one it is very simple, there is no stress risers, so the load will be equal to sigma max, because sigma max will be uniform throughout the cross section, everywhere it is the sigma max. That is what is the sigma max. Okay, actually sigma average, sigma max, everything is same because it is uniform over the section. So sigma max into area, that is what is the load. Okay, because the load, the stress that will be developed here, sigma, will be simply P divided by that area. There is nothing new in it. Okay, so this is what is the sigma max allowable in this particular case. Now we are solving this one. For this one, the sigma max, that is, you know, so you just put this sigma max as 80, that is given 80 megapascal, and you find out what will be this P, because this cross sectional area A, you know what will be this A. For this one, this will be D1 is the, it is a circular cross section, so it will be pi by 4 into D1 square. Okay, so this will be pi by 4 into D1 square. This is area of a circle of diameter D1. Okay, so in this equation, left hand side you know that is 80 megapascal, and the right hand side you know the area because you know the dimension D1, so you can find out P. So from here you can find out the value of P1 that is allowed. For the P2, what you do, obviously we'll search for the critical points. Critical points will be the stress risers. Around this point, if expected, the stress will be maximum. So we'll again use the formula. What is sigma max? Sigma max is KT into sigma nominal, right? So sigma max is again 80, because the same material. So it is 80. Remember, you have to consider the unit properly. It is in megapascal. So it is better that you just convert it into either kilopascal or properly convert, then you will get the proper unit of the load. And the KT values are given. So this one is known, this one is known. What about the nominal stress? For nominal stress, you know this will be the load P divided by this cross section, the smaller one, and that is equal to what? Pi by 4 d1 square. This is the circular cross section, so pi by 4 d1 square. Okay, so in the nominal stress you do not know what is P, so from this equation you can find out this P, and this P actually called P2 here, so you can find out this P. And if you see the result, you will find that the P2 is only 14400 kilonewton, whereas P1 is larger. So which one is stronger? This one is stronger, this one is weaker. So initially it was not so intuitive that this one will be weaker. Apparently it seems that this one will be stronger because the cross section you have enlarged, but because of the stress concentration, basically the stress at this critical point will be very high and material will fail if you go above this one, but this one can take up to this much. Okay, so this is what is the reason that even after enlargement of the cross section, this is not basically a strong component, rather this one is a strong component. Okay, so this much is there in your syllabus on stress concentration. So based on this video you have to solve a few problems that I will give you in the assignment. Okay.